Dear ladies and gentlemen, my name is Deborah Weiß and I come from Paderborn University in Germany. I am a member of the scientific staff of the group Applied Mechanics and I would like to give you a brief presentation of the topic Development of a special specimen geometry for the experimental determination of fracture mechanical parameters of clinchable metal sheets. First of all, here's my agenda. In the beginning, I would like to give you a short motivation why it is necessary to investigate the fracture mechanical parameters of clinchable metal sheets. Based on this, I will show you some numerical preliminary investigations which are necessary to carry out experimental investigations. In detail, I will present the special specimen geometry, the geometry factor function, and the calibration function. In the main part, I would like to present you the experimental investigations. These investigations are based on the influence of the anisotropy arising during rolling, where we have a look on the rolling directions along and across in relation to the initial crack. Furthermore, the influence of the mean stress sensitivity is analyzed. At the end, I will summarize the main points and give a short conclusion. Let's start with the motivation why this topic is important and became a project of the Special Research Area Transregio 285. In many areas of product manufacturing, constructions are made from individual components to more or less complex structures. Today we have many areas of applications where we have these more or less complex structures like energy systems, medical technology, appliances, or most common, the car manufacturing. Especially in the field of car manufacturing, lightweight constructions are very important. Focus on carbon dioxide emissions, the EU tries to reduce these emissions with legal regulations. For example, the carbon dioxide emissions have to be less than 60 grams per kilometer in 2030. This aim can be only achieved by a weight reduction of the structure. To do so, car manufacturers use multi-material design to get the best mechanical properties out of the materials. But these different material combinations make the joining process more difficult and limit the choice of the joining method. The complexity will be even bigger in the future because of the versatility of the assemblies due to different materials and combined joining processes. Since mechanical joining processes have so far been rigidly configured for the respective material geometry combination, the Transregio 285 deals with the method development for mechanical joining in versatile process chains. A joining method that can join different types and coated materials without additional heat input is clinching. Furthermore, you don't need a joining element, which leads to the desired result of cost and weight reductions. The clinching process will be explained on the next slide. Clinching, also known as press joining, is a high-speed mechanical fastening technique for point joining of sheet metal components. It is suitable for ductile metal sheets with thickness between 0.5 and 3 mm. Clinching requires no consumables or pre-drilled holes and is performed in a single step, making it an inexpensive and simple technique. A typical process cycle of this technique is shown in the illustration. The sheets are initially clamped between the blank holder and the die assembly, stage 1. The punch is then forced onto the sheets and locally pushes them into the die, stage 2. As the deformed sheets touch the bottom of the die, further downward movement of the punch forces the material to flow radially and form a button, stage 3. This material flow provides the mechanical interlock which holds the sheets tightly together. Finally, the punch is retracted, stage 4. As you can imagine from the process, there are many factors which influence the joint like the die, the joint parts, the punch or joining force, and the blank holder flaws. All these influencing factors during the joining process and due to the service load Cracks can occur in the area of the joint, like you can see in this picture of the grinding pattern of the joint. These cracks are the reason why we deal with crack growth in our sub-project within the GRR 285. We try to answer the questions: does a crack grow? How fast does a crack grow and in which direction does it grow? And when does the unstable crack growth start? In order to answer these questions, it is first of all important to determine the fracture mechanical parameters of the base material. To determine the fracture mechanical parameters of the base material, it is necessary to do some preliminary investigations. Therefore, I'm going to continue with the numerical preliminary investigations. According to the standard ASTM E647, a compact tension specimen, which is illustrated here on this slide, can be used for the determination of fracture mechanical parameters. However, due to the fact that very thin metal sheets are used within the clinching process, the development of a specimen with a special geometry is necessary. The normal mini-CT specimen is with 2.5 mm, 1 mm thicker than the used specimen. Due to the low sheet thickness, drill holes for the solder pins for potential measurement with a diameter of 0.9 mm are too large for frontal mounting. Furthermore, solder pins concealed by clamping forks when mounted on the side. Therefore, the ties were extended like you can see in the white picture. The stress intensity factor is a measure for the magnitude of the stresses and the displacements in the vicinity of the crack. It depends, among other things, on the crack location, the geometry of the specimen, and the type and location of load introduction. All these dependencies are considered in the geometry factor function. To prove what kind of impact the change of the specimen's geometry has on the geometry factor function, numerical calculations were executed with the simulation program Frank3D. Compared to the CT specimen, in accordance with ASTM E647, you can see in the graphic that the lengthening of the ties doesn't have a significant influence on the geometry factor function. Therefore, the numerical determined function in blue color will be used in the experimental investigations. A calibration curve describes the relationship between the potential difference and the crack length. This is important for the measurement of the crack length during the experiment. To define the calibration function numerically, I used the simulation program Abacus. There, a current is initiated and the potential is measured at defined nodes in different states of crack length. The determined function is illustrated in the graphic. After the numerical preliminary investigations, I'm going to continue with the experimental investigations. On this slide you can see the experimental setup. It consists of a tested specimen, a reference specimen, a PC with evaluation software, and a measuring device. The reference specimen is used to compare the initial crack with the crack length of the tested specimen during the experiment by means of the current potential drop method. The current potential drop method is a frequently used method to measure the crack length within a specimen. In this method, an electric current is introduced into the specimen and the potential difference is measured. With this potential difference and the help of the numerically determined calibration curve, which was explained on the slide before, the crack length can be measured. The principle is that the ohmic resistance increases by crack growth because of the reduction of the cross-section. To determine the threshold value, tests with a decreasing cyclic stress intensity factor were executed. This kind of test type is called down experiment, and for an example, the values for the first experiments are listed. Afterwards, tests with an increasing cyclic stress intensity factor were executed to identify the fracture toughness area. This test type is called up experiment. where the specimen, for example, is loaded under a general periodic load with maximum load of 600 Newton with an R ratio of 0.1 and a frequency of 10 cycles per second. This slide shows the results of the experiments with different rolling directions and an R ratio of 0.1. The rolling direction was examined along and across in relation to the initial crack. If you combine the performed up and down tests, you will get the crack propagation curves shown in these graphics. In general, 3 up and 3 down tests were carried out. It can be seen that the determined curves do not diverge from each other. Also, the values for the threshold and the fracture toughness are almost identical. In summary, it can be said that the rolling direction has no influence on the fracture mechanical parameters. The following slide shows the influence of the R ratio on the crack propagation curve. All tests were carried out with a longitudinal rolling direction. The comparison between the R ratio 0.1 and 0.3 shows that the fracture toughness is, with 46 megapascal square root meters on average, significantly lower at an R ratio of 0.3. However, R equal 0.3 has only a small influence on the threshold of R equals 0.1, but it is noticeable that the standard deviation of the threshold is more than twice as high as before, so it leads to greater fluctuations at lower crack speed. Since the database is still very thin, further investigations have to be carried out. On the next slide, we'll have a look at another R ratio. Further tests were carried out with an R ratio of 0.5, which is presented on this slide. To emphasize the influence of the R ratio on the crack propagation curve, the R ratio of 0.5 is compared to the R ratio 0.1. You can see that the curve with the higher R ratio shifts to the right. On the right side, you can see the general expected influence of the R ratio on the crack propagation curve, according to the literature for ductile materials. In general, the crack velocity increases with increase in R ratio. However, the influence is more pronounced in the low and high crack velocity range. Normally, the threshold value should be smaller with larger R ratio. However, in my investigation, that is not the case. A possible cause of the deviation of the examined curve from the theory can be plastification of the material, which might slow down the crack growth, especially in the threshold region. To validate this claim, a further test is carried out with a lower initial load. The lower initial load is intended to prevent plastification and, hence, sequence effects at the beginning of the test. The graphic shows that the curve at lower initial load deviates significantly from the previously established curve, both in the area of the peristraight line and the threshold region. A comparison of the results from the experiments with an R ratio of 0.1 on the right side illustrates that the curve tested with an R ratio of 0.5 and lower initial load shifts to the left. The result corresponds to the aforementioned theoretical principles. To put it all in a nutshell, the crack velocity increases with increase in R ratio and the threshold decreases. Ladies and gentlemen, now I want to conclude by summing up the most important results. First of all, the topic of this presentation was to develop a special specimen geometry to determine fracture mechanical parameters of clinchable metal sheets experimentally. After the numerical and experimental investigations with the special specimen geometry, it can be stated that this geometry is suitable for crack growth tests. Furthermore, the experiments of the rolling direction show that the anisotropy arising during rolling has no influence on the fracture mechanical parameters. Finally, the crack velocity increases with increase in R ratio in accordance to literature. To validate these results, further experiments with an R ratio of 0.3 must be carried out to describe the mean stress sensitivity correctly. In addition, there must be further experiments with an R ratio of 0.5 and lower initial load to prove the assumptions made. Furthermore, in the future, clinchable components will also be tested. In the end, I thank you for your attention, ladies and gentlemen. I hope you have enjoyed my presentation. If there are any questions left, do not hesitate to ask or send me an email to the given email address.